This is an introduction to using the optimization features of ADS. And what you can see here on screen is an LNA project that I was working on recently for homework. I've got just a basic common source LNA here. There's a cascode MOSFET. And the important thing to note here is that I have all the basic components that I want in the final circuit. As well, in this case, what I'm going to try and do is optimize the input and output impedances of the port. Eventually I want to match it to 50 ohms, but for now I'm going to try and match whatever the optimal port impedances are to meet my specs, and then later match them to 50 ohms. So here, for example, on the input port, you can see I've actually, rather than defining it as 50 ohms, defined it as P1 real plus J times P1 imag for the impedance of the port. And the P1 real and the P1 imag are actually variables that I've defined in ADS. So here you can see I have this var block for variable, and I have W1, W2, which are the widths of the MOSFETs in the circuit, and then I have the P1 real, P1 imag, etc. Here they have rather arbitrary values. It doesn't matter. For now I'm going to optimize them, but I just needed some sort of value in there to begin with. W1, W2, I picked those just because of previous experience working with the LNA, and I think that's a good starting position. When you're using the optimizer, it's a good idea to get at least a basic starting circuit, and then the closer you can get to the final product, the better the optimization will work. At least that's in my experience. So in this case, what we're going to do now is take a look at this optim block that I put in here, and as you can see here, I've got box checked here. We're going to use all goals in design. I'll show you those shortly. And then the other important thing to note here is I've used all optimization variables in the design. Down here you can see I've set just a massive number of iterations. I don't really care how long it takes. I want it to get as close as it can to my goals. The other important thing here is I've got the quasi-Newton optimization type. By default, it's going to want to go with random. I've had better luck using either the quasi-Newton or the least PTH here as well. Has worked well for me. So we'll go ahead, click OK. Let me double check here. I don't think there's anything else we need to set in here. And besides using this optim block, we're actually going to need goals as well. So here you can see I have goals for my S parameters and goals for my noise factor. I'm going to pull up the noise factor one as an example here. And you can see the expression that I'm trying to optimize is NF of 2, so the noise factor here. And I've said that NF spec, that's just an arbitrary name I've given to the line, needs to be less than 1.5. So basically what I'm saying is that the noise factor needs to be less than 1.5 dB is the parameter that's returned from NF2. The frequency min here and max, I've set not too skinny of margins, but a skinny area of where I'm actually interested in having that parameter met. So in this case I've got, what is that, 4 megahertz bandwidth that I'm trying to optimize it across to make sure that that noise factor is always below 1.5 in that region. So the same sort of thing applies here. I've got equations for the S parameters as well. Now with that said, in my case I'm doing optimization with the S parameters, so I have this S parameter block as well. I basically told it to start at 2.3 gigahertz, stop at 2.5 with a step size of 0.5 megahertz. So I've got 401 points. That should work fine for what we're doing. Now for the actual exciting part. Now that I've got everything picked, what I can do is on the actual individual components, each one of these has an actual like acceptable optimization range. So for components like the capacitors and resistors, I've actually got that set in here on the optimization tab. I've got it enabled, and then I've set a minimum value of, in this case, 0 farad, 0 picofarad, and then a maximum of 20 picofarad. Be aware that the optimization will complain when you're setting these if you don't have them both in the same units. So make sure that, for example, I need 0 picofarad, 20 picofarad, and then I'd also need to make sure that this value here is in the range that's set in the optimization, or it'll give you some kind of error. So I'll apply it in this case, hit OK, and the same sort of thing applies for our variables here. I'm going to say, for example, the width, I probably don't want it any skinnier. In this case I just set it to 1 micro, but I definitely don't want it any wider than 250 for now. So I set those. I'll hit OK, apply, and I've basically done that for all my components specified an acceptable range. And note that, for example, here where the bias I've already set and I don't want it changing, I don't have any optimization available here, so it can't mess with that. So now what I'm going to go ahead and do is click the optimization button. I've already set the settings in the Optim box that we looked at earlier. That's this guy back over here. And note that in here we said use all goals in design. If you needed to, you can actually say I only want, for example, the Optim goal one for me is that noise factor requirement. I could say only try and meet that requirement. The same sort of thing applies for the variables. That comes in really handy if you're trying to match something and you only have a certain number of components that you can change the values on. In this case, I could say I only want to mess with L11, L10, C8, C7, and leave everything else constant, even if it was actually set to be able to be optimized. So in this case, I want to use everything, and I also want to use all goals in the design. So I'll click OK. I'm going to zoom out here and go back to the schematic. And now what I'm going to do is click the Optimize button here. And initially, you can see we are nowhere close to meeting our requirements here. Conveniently, we've got this little indicator that kind of shows where we're at on meeting our goals, and you can see the current values of each of the components that I said it could optimize. And it's rather amazing to watch, but what happened is initially everything was horrible. It's still horrible. You can see here based on which goals are being met, but as it's going, ADS is actually getting closer and closer to optimizing the component values into actually meeting spec. In this case, for example, I wanted a noise factor of less than 1.5 dB. Some of the S parameters need to be less than 12 dB or greater than 12 dB, depending on which ones. And as you can see, it's sort of tuning. This little dip here is getting closer to the red dot. That red dot represents what I'm actually trying to meet. So in this case, if I hold my mouse over it, for example, this tells me that at 2.389 or 2. It's moving here. The gigahertz spec that it's giving me right there, it gives me the accompanying response. And then the red dot there is that area that's actually specified in the goal. So that width of the red dash there is the width that I'm actually trying to get it to meet spec in, and the actual vertical position is the vertical position of the spec. So for example, in this case, I'm trying to get negative 12 dB, I think is what I wanted in here. So you can see it's kind of tuning the parameters. In this case, it's actually got my noise factor, it looks like, if I hold my mouse over right in the frequency zone. No, not quite. It's getting close, though. We're at 2.4 gig, roughly, and a frequency response, or noise factor response of about 1.58. It's getting closer. At this point, you can see all these other ones are pretty much optimized into where I want. Amazingly, this has only taken 24 iterations to go from some horrible piece of junk to something that's actually getting very close to meeting spec. At this point, you can see up here, really the only parameter it hasn't matched yet is the noise factor, and it's going to keep messing with it. Unfortunately, sometimes if you gave it unrealistic goals or it's just not feasible, eventually, rather than just iterating 100,000 times, it'll actually give you a note up here that says like no further improvement possible. In that case, I've just manually tuned some values and started it again. Like I said earlier, this is the quasi-Newton approach. I've had good luck with it. The least PTH one worked well for me as well. So much better than the random guessing that you can do as well. And in this case, you get a feel for kind of what it's doing. You can get some history here on what the component values have been. And in my case, what was important was knowing what the optimal port impedances are. So here you can see on the port 1, which is my input port, it's slowly kind of fine-tuning it down to an imaginary component of plus 25J, and a real component of about 1 ohm seems to be about the perfect value for getting the best noise factor, or noise figure in this case, and meeting my S parameter specs. So that's kind of an introduction and should give you a good idea of what to do. I haven't used the optimization parameters very long and that functionality, but I've been really impressed. It's worked really well. So good luck and have fun.